السلام عليكم ورحمة الله وبركاته.
وعليكم السلام ورحمة الله وبركاته. How are you, Doctor?
Yeah, I'm fine. What about you?
I'm fine, Doctor. Thank you.
Yeah, okay. So let's move on. Today we'll start the last chapter for the course, which is water distribution system or flow in pipes, which is on distribution systems, okay, and the intended learning outcomes. Students will be able to, at the end of the presentation, analyze pipe friction losses and minor head losses, analyze a pipe network using the head cross method, and design a simple water distribution network. Okay. If you remember, this is from chapter 1, where we discuss about the water resources development. Okay. And these are the distribution system components. And the figure presents the conceptual layouts of two water supply systems. Okay. One, the impounding reservoir, and then you have like a dam. Okay. And then have water impounded or collected in reservoir. And then you have conveyance conduit, which is the pipe conveying to the treatment plant, and then service reservoir, and then to be pumped to the distribution system, which is the CT. Okay. Same thing, this is from a well field, okay, or from river intake to the treatment plant, and then to the service reservoir and to distribution system. So at the end, what you have is distribution system, or what we call water distribution system, or the pipe network, okay, or distribution or pipe network, or pipe water distribution network, okay, which is how the water is reaching the end users. You can imagine the distribution network here to be like the Bathing City, okay? All these are pipes, passing across, the roads in front of buildings, houses. You can imagine all these grids to consist of houses where they can tap from the pipes passing across, okay? So, and this is where we are going now to dwell. This is what we are going to be considering. Okay. At the beginning, we look at flows in like rivers. We analyze the flows, normal flow, and how to measure the flow. And then the treatment plant is taken care of by the environmental engineering section, CE330. Okay. That is when the water reaches the treatment plant, what happens, all the unit operations, the processes from, the flow, coagulation, sedimentation, or even flotation may precede that, depending on the water quality. And then from there to sedimentation, then to filtration, from filtration to disinfection, from disinfection, you now, convey it again. You pump it to the service reservoir and then to the distribution system. Okay. So now we will look at pipe flow. Like, how can you pump water from the river to the distribution to the treatment plant? Okay, using a pump. And then we will look at now how does the water move from the treatment plant to the distribution network, and what is the analysis of flow in the distribution network? Okay, we only isolated the treatment plant now. Okay, and why did we isolate the treatment plant? Because that is taken care of by the environmental engineering aspect. Okay, in which they will have a given flow rate. Okay, the Q, and then they will use that to design the treatment processes. Okay, which CE330 has taken care of. Okay. Now, distribution system components. At or near treatment plant, the pumps that lift surface water and move it to the treatment plant are called low lift pumps. This we explained before in chapter 1. Okay, we call them low lift pumps. The pumps that lift from the, at Onia treatment plant that lift surface water and move it to the treatment plant, let's say from rivers, streams, or lakes to the treatment plant are called low lift pumps. And this move large volumes of water at relatively low discharge pressure. Okay, and that's why they are called low lift. Okay, they lift large volumes of water at relatively low discharge pressures. Okay, at relatively low discharge pressures. And this from a treatment facility, water is transferred to a water storage facility using feeder mains and the pumps. Okay, and these pumps that transfer water from the treatment facility to the feeder mains. Feeder mains here may refer to the distribution system, the storage facility, and all that. Okay, the pumps that discharge treated water into the storage facility are called high lift pumps because they operate under high pressures. Okay, because usually the water storage facility, you realize that they are at certain elevation, sometimes at elevated position in the town. Okay, so you need high pressures. Okay, high pressure pump. So here we use high lift pumps. And the design consideration for the high lift and low lift pumps are already considered in chapter 1. Okay. From a water storage facility, such as a reservoir, from a water storage facility, such as a reservoir means just, a huge tank, or a tank or a tower, water tower. By tower, it means it is elevated, it is above the ground, the tank is above the ground. Okay, so it's supported by a tower. Okay, that's why it's called a tower. Water is carried through a network of pipes for distribution to consumers. And this is exactly what we have here. Okay, low lift pumps, they pump to the treatment plant. High lift pumps, they extract water to the service reservoir. Okay, then from the service reservoir to the distribution system. This is simply describing that figure. It's carried for distribution to consumers. The pipe network may be of a grid or branching type, okay, or a combination of the two. The grid is a closed loop. Grid is simply what we have here. This is grid or loop. We call it loop or grid because this is like a grid system. Okay, and you have branching type. Branching, it means, it branches, just like tree. Okay, you have some branches, not closing up because loop is closing up. Okay, so these are like branching type. Okay, all these are pipes and these are knots. Okay, and sometimes you have combination of the two. You may have a branch network together with a grid network. Okay, we're going to analyze the pros and cons of each one. Okay, for the closed loop system and the branching system. A branching system has numerous terminals or dead ends that prevent water from being circulated throughout the system. It has dead ends, and these dead ends, they prevent water from being circulated throughout the system. If you look at this, if you consider this point, okay, I will sketch something here. When you have the grid system, let's say you have this grid, okay, and this is the inflow, okay. You can see this point, this node can receive water from this pipe or from that pipe, okay. So you realize that all nodes are receiving water from at least more than two pipes, okay. So that makes the water to be completely circulated within the system. But when you have a branch network, let's say you have this, you have this, you have this, you have this, a node at this point the people extracting water will only receive water from this pipe. Okay, if there is any problem, a maintenance that is taking place along this pipe in which the flow to the pipe is shut by a valve, there will be no water in the pipe, and the people relying on this node will not have water. Whereas if you look at this node, if this pipe is taken out for repairs, is shut down for service, this node will receive water from this pipe. Okay, so you realize that the node will not be without water at any point in time. Okay, and these are called dead ends because they are not connected to any other pipe. Okay, all these nodes at the end, they are dead ends because they are not continuous, they are not connected to any other one. Okay, we call them dead ends. I'm having headache this morning, so, and as I am talking, I'm feeling, my head is really reactive. So I will be talking gradually, and let's see how much we can cover. Okay. The grid system is preferred because it can supply water to any point from at least two directions. You can see this exactly what I was mentioning, because it can supply water to any point from at least two directions. But of course, you can see that the grid network is more expensive because you'll have many pipes. Okay, so it's more expensive. The branch network may be less expensive. Okay, but it's, again, sometimes it depends. For rural water supply in which the inhabitant is the population is not so much, the branch system is better. When you have few population to supply water to, but for a municipal water supply to a big town, then the grid system is the best. Okay, so the grid system is better, which we call the loop system. Okay, because it can supply water to any point from at least two directions. Okay, so this is like an example. Like I told you, you can see that, you can see the buildings here. Okay, all tapping. It is expected that outflow of water from the pipe is occurring only at the nodes. That is the joint where two or more pipes meet. Okay, so you can see all these houses can tap water from this node. These ones can tap water from this node. This one can tap water from this node. Okay, but this is a branch network. For smaller towns, the branch network is good. Okay, but for bigger towns, then the grid network is better. You can see this will receive water from this one and from this one. Okay, this will receive water from four directions, almost four directions. Okay, so if any one or any two of the pipes are taken out for service, the node will still receive water from the other pipes. Okay, so you can see even from here, the grid network entails having more pipes. Okay, so it is costlier. It is costlier, but at the end, customers will always be having water in their pipes. Okay, so the grid system also permits any broken sections to be isolated for repair without disrupting service to large areas of the community. This I just mentioned. So a combination system is the type most commonly used. Okay, so you have combination system, okay, which is the type most commonly used. And as we are going to see in the pipe network design, okay, more often than not, we neglect service pipes, because like here you can have buildings in which they can have service pipes coming in, going there, which will be some sort of branch system. Okay, so more often than not, you have combination of the two systems. Okay, but for design purposes, normally we look at the mains, the service mains, the main pipes. Okay, the main pipes meaning the bigger pipes bringing water from the service reservoir. Okay, which are very big. The diameter usually 12 to 10 inches. Okay. Still on the distribution system components. We have additional water pressurizing components like pumping stations, which are situated or located at various points of the distribution system where pressure boosts are needed. As water flows in the pipelines, they lose energy. I mean, there is head loss. Okay, the pressure head reduces as it is flowing in the pipelines. So sometimes, depending on the distance, there is need to boost the pressure. Okay, that is to increase the pressure, because the more the pressure head, the more the water can reach, the tallest building in the area. As we are going to see later in the design of the pipe distribution network, normally we design such that the pressure head should be able to reach at least around 4-story building. That is, if you have a pipe, if you have a pipe, the pressure head should be able that when you now, extract water, when you suck your pipe, it will reach about 4-story building. And this is so high. Okay? And if the pressure head is not enough, it cannot reach that point. Okay, so sometimes there is need to boost the pressure. Okay, and that's why we have pumping stations. And all components from the point of treatment onward constitute a distribution network that is a pressurized system. Okay, all components, okay, from the point of treatment onward, okay, constitute a network. They constitute a distribution network that is pressurized system. Okay, it has to be pressurized because we use pipes. Okay, we use pipes. Although the pressure can result from gravity. Okay, we can have a service reservoir, a tower, okay, which will now be elevated. So by elevating it, it will have a lot of pressure. The potential energy of the water will be high, thereby increasing the pressure head, that when the water is supplied to pipelines, it will have adequate pressure head to reach the consumers. Okay, but we use pressurized system for water distribution network. Don't forget, we mentioned that for sewer distribution network, we use open channel. We use open channel. We can as well use pipes, but the pipes do not flow full. And if they don't flow full, it means they are treated as open channel flows. Okay, don't forget this. And these components include piping, pumps, storage tanks, fire hydrants for fighting fire, service connections, and meters. Service connections, the small pipes that, extract water to the various residential areas, to the various housings and buildings. And meters, water meters, for metering the amount of flow, the amount of the amount of the volume extracted by individual, so that that can be used to pay for the water cost. And of course, we have other components like the valves. The valves are very important. Okay, we call them, appurtenances, pipe appurtenances, the valves, the connectors, and all that. Because the valves, there are ones that are installed at intervals to ensure that the water flows in one direction. Okay, you need to ensure unidirectional flow of water, and there are ones, for in order to take, if there is need to take a particular pipe out of service for maintenance, for any repair work, so there are different types of valves that serve different purposes. In order to function properly, a water distribution system requires several types of fittings. I just started mentioning them. Okay, hydrants, shut-off valves, other appurtenances. We call them these fittings. We call them appurtenances. Okay, appurtenances. You have the valves, you have the hydrants. The main purpose of hydrants is to provide water for firefighting. They also are used for flushing water mains, okay, and pressure testing, okay, to test the pressure in a given pipeline, and water sampling, okay, if you want to take the sample of water at a given location to go and test the water quality and make any other test that we deem fit, and washing debris off public streets, okay, you can use it to clean the streets. Now, the piping system. We'll consider each of the components of the water distribution network. Okay, the piping system is comprised of pipes, valves, and fittings. Pipes must be able to resist internal and external forces as well as corrosion. Okay, corrosion is one of the processes that take place in pipes, okay, which can damage the pipe, okay. So that is why the internal, surface area of the pipe is usually coated, because pipes are usually made of sometimes steel. Steel is susceptible to corrosion depending on the quality, okay. So you usually have it lined, okay, lined with non-corrosive material, okay. You have different pipe materials: ductile iron, plastic pipe. Plastic pipe is not susceptible to corrosion, but then plastic pipe cannot carry high pressure. Okay, we can use plastic pipe, let's say, for service connection within the house, and because they don't carry high pressure or high flow. Okay, but when you have high flow, you need stronger pipe material. Okay, like ductile iron, like steel material, and all this. Okay, and all these are susceptible to corrosion. Okay, both in so the pipe must resist internal and external forces. Internal forces will be due to the water, because the water has power, okay, it has momentum. And external forces, pipes are usually buried underground, okay. So you have the weight of the overburdened soil, okay, and sometimes, a lot of cars, trucks, and all that can be passing over it. So the pipe needs to resist both internal and external forces. Water pressure inside the pipes, the weight of the overlying, I just finished mentioning it. The weight of the overlying soil, the vehicles passing over them place stress on pipelines. Pipelines also may have to withstand what are known as water hammer forces. When you close a valve suddenly, okay, it sends back, pressure wave upstream, and that pressure wave can be so disastrous that it can destroy the pipe itself. Okay, so pipes have to withstand water hammer forces. Okay, water hammer forces more or less like decreasing the density of, because when you suddenly close the valve, the water at that section is locally compressed, okay, thereby reducing its density, okay, and that sends shock waves upstream, okay, and you hear a sound like as if the pipe is being hammered with a hammer, okay, gang, okay, and that is because of the shock waves, okay, the pressure that will be propagated upstream, and that pressure can damage the pipe. Pipes are made of cast iron, I just finished mentioning, ductile iron, plastic, reinforced concrete, or steel. Pipe sections are easily joined with a coupling sleeve and rubber ring gasket. Okay, these are the pipe fittings used to join, one pipe with another. Because pipe, they come in some standard lengths, so you need to join them to, have a long pipeline. Many types of are used to control the quantity and direction of water flow. Okay, one of them is called gate valves. Okay, gate valves are usually installed throughout the pipe network. They are called gate valves because just like a gate, it allows the flow in and out of, let's say, cars, inside your apartment. So the gate valve also allows water to flow in and out, okay, of the pipeline. They allow sections to be shut off and isolated during the repair of broken mains, pumps, or hydrants. Mains here, like I mentioned, they refer to the pipeline, that are laid that convey water from the treatment plant, from the storage facilities to the municipal areas. Okay, so they are the biggest pipes. Okay, so that's why they are called mains, primary pipelines or mains. Energy equation of pipe flow. Here we'll still go back to our fluid mechanics, what we have been doing, the energy equation, the continuity equation. Okay, we will still not leave these equations. Okay, energy equation and the continuity equation. And here we will just briefly explain the hydraulic grade line and the energy grade line, which you must have been taught in fluid mechanics. Okay, so we'll go over them briefly because they play important role. Okay, because like I told you, when water is flowing in a pipeline, it loses energy. Okay, due to the frictional forces shear stress acting on the walls. Okay, and pipe flow is an internal flow because it is bounded by the pipe material from all sides. So it is an internal flow. So you have, the head loss to be high. Okay, and when you have the head loss, then we will have to balance it using the energy equation, which is simply a statement of the conservation of energy. Okay. Now, what is hydraulic grade line? Hydraulic grade line, it shows the elevation of pressure head along the pipeline. Okay, pressure along, it shows the elevation of pressure head along the pipeline, or simply the flow pressure. Okay, that is, it is a line connecting the points to which the water will rise in piezometric tubes inserted at different sections of a pipeline. If you insert a piezometer, the height to which it will rise, okay, indicates the pressure head. Okay, it indicates the pressure head. Yeah, this is a pipeline. You have flow of water in this direction. Okay, so if you insert, the water that is flowing possesses pressure, isn't it? So if you make a small hole here and insert a tube, okay, water will rise up to a level, up to the level of the piezometric head. Okay, so in this case, water will rise up to this level, and that indicates the piezometric head. Okay, that is the P1 at the center. Okay, P1 over gamma, which is the piezometric head. The same thing here. You can see the piezometric head here is different from the piezometric head, that it has dropped because of the energy loss, because of the head loss, which is mainly due to friction. Okay, we have other minor losses, but the main head loss is due to the friction, the shear stress exerted, or the frictional force exerted, by the pipe wall on the flowing fluid. Okay, it causes energy to be lost. And that is why the piezometric head is decreasing along the flow direction. Okay, it's decreasing along the flow direction. So this is P2 over gamma. P, is the static pressure, as we all know. It is the static pressure. Now we have the velocity head, which is V squared over 2G, which is the velocity head. Okay, and as we explained, the velocity head is simply the dynamic pressure. Okay, is simply the dynamic pressure, which is because of the dynamic effect, because of the kinetic energy of the flowing fluid. Okay, because of the kinetic energy of the flowing fluid. So, and is dependent on velocity. Okay, this is a uniform pipeline. So probably if the velocity remains constant, that is, you have a uniform flow, then it will be the same. Although you have the velocity reducing gradually here, you can see the height of the velocity head is lower here. Okay, it is lower, which indicates that V1 is not equal to V2. Okay, but sometimes if we assume uniform flow, for uniform flow, the velocity will be constant. Hence, the energy grade line will be parallel to the hydraulic grade line because the velocity head is the same. We call it energy grade line because here we are taking care of the energy, the dynamic energy. Okay, the dynamic energy. And this is the highest level as far as the Bernoulli principle is concerned. Because for the Bernoulli principle, we are assuming that there is no head loss. Okay, we are neglecting losses. So in that case, we are saying that the elevation head plus the pressure head plus the velocity head is constant along a pipeline. Okay, so if we are to apply the Bernoulli equation here, it means we are going to neglect the head loss, which is HF. Okay, which is HF. But in practice, for most practical cases, you realize that head loss is not negligible. Okay, for most practical cases, you realize because of the shear, the viscous effects, because of the viscous effect or the shear stress or the friction. Okay, and that's why here we call it head loss due to friction. The head loss is not only due to friction, we call it head loss head loss because the head is being lost. This is the pressure head. The pressure head is being lost. It's decreasing. Okay. And why is it decreasing? Because the head loss is increasing. Okay. So the head loss is normally because the main process causing the head loss is the friction. Okay. So HF plus HM. HM is the minor losses. Okay, minor losses are losses that occur at bends, change in pipe section, when you have a pump, when you have a valve, all these, there are minor losses. But all these losses, more often than not, are very small compared to the friction loss. Okay, so that's why usually we consider the friction head loss, okay, and neglect the minor losses. In the design, we are going to see in our analysis, okay, where we will consider the minor losses. Okay. And here we call it the SF, the energy grade line, which is the slope of the friction head loss. Okay, this is called friction slope or energy slope. Okay, SF. Okay, and the slope is due to the frictional force or frictional head loss. Okay, and that is why it is simply defined the frictional slope as the head loss occurring within the pipe length. Okay, is the head loss occurring over the entire pipe length. Okay, so the definition of SF is HF over L. Okay, and the definition of S naught, which is the bed slope, we call it bed slope. Okay, in this case, it is the change in elevation of the pipe. Okay, divided by the difference between the 2 points. Okay, not actually the pipe length, but let's say over delta X. Okay, delta X is the distance between the 2 points, which is this. Okay, and this is delta Z, which is the difference in elevation between the 2 points. Okay, for uniform flow, you realize that S naught and the top of the water surface, we call it SW. Okay, for uniform flow, you realize that the bed slope is equal to the water slope and is equal to the friction slope or the energy slope. Okay, because more often than not, you realize that delta Z is usually very small. So for that, you realize that HF over L is simply tan, let's say tan theta, if the angle of inclination here is theta. Okay, it's usually tan theta. Okay, and S naught is usually sorry, this is tan theta and this is sine theta, because this is sine opposite over hypotenuse, so this is sine. But for small angle, for small theta, you realize that sine theta is equal to tan theta. So SF is equal to S naught. This we explained before in our previous lecture. But you need to understand this figure very well. When you use a piezometer, water will rise to this level. What about when you use a pitot tube? Water will rise to this level. When you use a pitot tube, because the pitot tube measures the velocity head. Okay, if you use a pitot tube, water will rise to the level of the energy grade line because the pitot tube measures the velocity head in addition to the piezometric head. It gives you the sum of the static pressure and the dynamic pressure, okay, which we call the stagnation pressure. Okay, so when you use a pitot tube, water will rise up to the level of the energy grade line. Okay, but water will not rise to this level, okay, because of the head loss. Okay, because as water is flowing, it is losing the head, it is losing energy, okay. Let me go back, and with this few explanation on this, now the energy grade line, it represents the total head. The total head means the elevation head plus piezometric head plus velocity head. And I hope now you understand what is meant by the piezometric head. Let me even go back to the figure. And, this piezometric, not piezometric head, but pressure head. This pressure head, the height to which water will rise when you have a piezometer, this could be, it has to be, you can imagine if you have, let's say, this is one-story building, okay? And the piezometric head is up to the highest level. It means that your bathroom on the first floor will have enough water because the water will rise up to the top of the building, okay? But what about if you have three-story building? If you have three-story building, let's assume this is a three-story building. This is the height of a two-story building. Okay, that is 3 floors. Okay, this is the highest level that water can reach. But now this is the level of your toilet. It means water cannot rise up to the level. You cannot take shower. Okay, you cannot take shower because the pressure head is not enough. Okay, and that is why, in pipe network design, we need to ensure that the pressure head is enough within the pipeline. And we are going to explain what are these pressures. I mean, the pressure head. What is the value of the pressure head that will be enough in a given pipeline? Okay, I just want you to understand like the physical interpretation of the pressure head. Okay, the pressure head, which is the height to which water will rise. Okay, the height to which water would rise. Okay, if there is no enough pressure head, then it will not rise to the tallest building, to multi-story building. But if you have enough pressure head within the pipeline, it means water could rise up to the tallest building. Okay, now the energy grid line represents the total head at different points of a section. In a uniform pipe, the velocity head is constant. This I mentioned. Okay, thus the energy grid line is parallel to the hydraulic grid line. That is in a uniform pipe. Okay, but if it is not uniform, because once the velocity changes, it means that the velocity head is going to change because the velocity head is simply v squared over 2g. So when the velocity in the pipeline increases or decreases, okay, if the velocity increases, the velocity head will increase. If the velocity in the pipeline decreases, the velocity head will decrease. Okay, we are going to expatiate more on this. So applying the energy equation between points 1 and 2 gives us the energy equation, which is an extension of the Bernoulli equation. The Bernoulli equation does not incorporate head loss. So the energy equation is now like a more balanced equation, an extension of the Bernoulli equation, in which, it is incorporating the head loss occurring at, within, when you have 2 points, when water flows from one point to another, there is definitely head loss. Okay, so that head loss is mainly due to the friction, HF. Okay, that's why from point 1 to point 2 you have HF. Okay, so this will make the total head to be the same. Okay, if you incorporate, elevation head, pressure head, velocity head, and then the head loss. Okay, so it means you will always have a horizontal line in this case. Okay, which is the total head. Now, energy equation of pipe flow. Okay, I already mentioned, HF is the loss of head along the pipeline due to friction, and the energy gradient is SF equal HF over L, which is the head loss per unit length of the pipe. And like I mentioned earlier, we have additional losses resulting from valves, fittings, bends, and so on. And these all are known as minor losses and are designated using HM, okay, minor losses, and have to be included when present. They have to be included when present, except that for some simplicity, sometimes you know, because as the name implies, they are minor compared to the major ones. The major one is the frictional head loss. Okay, so sometimes they are neglected because more often than not, they may not change the computations a lot. Then the term HF will be replaced by the total head loss, okay, which is H loss. So meaning H head loss is simply the sum of the frictional head loss and minor losses. Since the minor losses are localized, meaning they are at a given line, the energy grade line represented by HF over L will have breaks. Okay, it will have breaks wherever the minor losses occur. Okay, meaning whenever you have the minor losses, the energy grade line will have breaks because it means H is going to change. Okay, H is going to be affected. Okay, H is going to be affected. It's no longer HF, but there will be, it will take care of HM. Okay, we will expatiate this with some. And if mechanical energy is added to the water by a pump or removed by a turbine between the 2 points of interest, it should be added to or subtracted from the left side of the equation. Pump adds energy. Okay, pump adds energy. Okay, so we should add it to the right side. And turbines subtract energy from the moving fluid. Okay, it subtracts energy from the moving fluid. So pumps should be subtracted and turbines should be added. Okay, since it subtracts the energy. Okay, so it should be added. All this we are going to see exactly how to incorporate them using an example. Okay, when we add a pump, when we have a turbine. Now let's take a simple example here. Example 12.1, which in our own case, using the latest version, it will be 15.1. It will be 15.1 because from a reservoir, it says from a reservoir, water flows at a rate of 10 cubic feet per second through a pipe of 12-inch diameter, as shown in figure 12.2. Determine the head loss, determine the loss of head in the system. This is it. This is the reservoir and water flows. This is the difference in height between 0.1 and 0.2. Difference in head 40 feet. And this is the datum 0.2. And this is 12-inch. Okay, that's the diameter of the pipeline. Okay, so we want to determine the head loss in the system. So the head loss in the system will be determined using the Bernoulli energy equation. Okay, we consider 2 points. You know, pressure is atmospheric, so 0. And we can neglect the velocity, the initial velocity at the first point. Okay, because it's very small compared to the velocity in the pipe. Okay, so to find velocity in the pipe, we find the area of the pipeline, pi d squared over 4, and then use the continuity equation to get the velocity. Okay, and then consider the datum. Here v1 is 0, so here we can find the head loss. Okay, and this is the head loss due to friction. Here we do not incorporate minor head losses because here at the entrance there's head loss, entry head loss. As the water is entering, there is head loss here. Okay, if I want to sketch, let's say, a sample of, ideally, this is the total head. Okay, but then because of the losses, here there is entry loss. Okay, within the pipe, so the both the pressure head and the velocity head will rise here. We'll start from here. If this is the velocity head, sorry, the top of the SF, so SW, let me say it's parallel. Let me assume the velocity is constant. So this is SW, which gives the pressure head, and this is SF, which gives the velocity. So this is now the velocity head. Okay, the difference between SF and SW is the velocity head, and then this is HF, head loss due to friction. You can see as it is flowing, the head loss is increasing. Okay, it is increasing. So this is the total head loss due to friction. Okay, we neglected minor losses, of course. Now, pipe friction losses. Here we will analyze this head loss. Okay, pipe friction losses, and we will use the two commonest equations, that's Westbank equation and the Hazel-Williams equation. Okay, the Westbank equation is the most general formula for the pipe flow application. It was obtained experimentally. Okay, however, Chase's equation derived, which we derived before from balancing the motivating and drag forces on the moving water, can be reduced to the Darcy-Weisbach equation. Okay, but the Darcy-Weisbach is actually an empirical equation which was obtained experimentally. Okay, so here we can start from the Chase equation, V equals C into square root of RS, and replace S with HF over L and R with D over 4. You remember we derived that the hydraulic radius is D over 4 when you are dealing with pipe, isn't it? And then the Chase constant, you replace it with C equals square root of HG over F. So if you do that, you will end up with the Darcy-Weisbach equation, which is F L over D, V squared over 2G. L is the length of the pipe, F is the friction factor, okay, which is a constant and is dimensionless. Okay, and HF is the head loss due to friction in pipe. And then D is the internal diameter, and V is the mean velocity of flow. So here it implies as the velocity increases, the head loss increases, isn't it? Because if you see the head loss due to friction is proportional to V squared. Okay, it's proportional to V squared. And as the velocity within the pipe increases, the head loss increases. Now, the solution of this equation, of the Darcy-Weisbach equation, we simply write it as dW, d-w, Darcy-Weisbach equation, dW equation. Okay, so the solution of the dW equation requires the interim step of ascertaining an appropriate value of the friction factor to be used in the equation. Okay, we need to determine the friction factor, which is dimensionless. Okay, and the friction factor for Darcy-Weisbach equation, how do we find it? That will take us to what is called the Moody diagram. Now, the friction factor relation depends on the state of flow, which is classified according to the Reynolds number. State of flow, which can be laminar or turbulent. Okay, for pipes, the diameter is used as the characteristic dimension, and the Reynolds number, as we know, is VD over more. Okay, for open channel, you know, the characteristic dimension is VR. We use the hydraulic radius. Okay, for open channel. For pipe, we use D. Okay, and we know that for pipe flow, when R equals to 2000, then or less or equal to 2000, this is a laminar flow. It's corresponding to laminar flow. And for R greater or equal to 4000, this is turbulent flow. Okay, and for R in between 2000 and 4000 is called transitional flow, meaning it is transitioning, changing from laminar to turbulent. Okay, so this is the state of flow. We use the Reynolds number to determine the state of flow. Now, another formula of the friction factor of the friction head loss is called Hazel-Williams equation. We abbreviate it as HW. The other one DW, that's Westbank, DW, and this one Hazel-Williams. It's also another common formula for the head loss in pipes that has found, almost exclusive usage in water supply engineering, and it is also empirical. This is based on this is the metric units. Okay, C is the Chesy constant. It's called Hazen-Williams coefficient of roughness, which is similar to the Chesy's coefficient. Okay, and R is the hydraulic radius. S is the slope of the energy gradient. Okay, S is the slope of the energy gradient, which, depending on the angle of inclination, depending on the bed slope, it can be approximated as the bed slope when the angle of inclination is, when this bed slope is very small. And then this is the velocity, which we can convert to the equation using the discharge by saying V equal Q over A, and the area for pipe is pi d squared over 4, and R is d over 4. So when we substitute R equal d over 4 here, and V equal Q over A, and simplify, we will get the equivalent flow rate equation of the Hazen-Williams formula for pipe flow. Okay, and this is, the flow rate equation, where D, that is in terms of the diameter and the energy slope. Okay, the slope of the energy gradient. C is the Chesy's constant. At R equal 1 and S equal 1 over 1000, the Hazen-Williams coefficient C is the same as Chesy's coefficient C. Okay, so at this condition, when R equals 1 and the energy slope is 1 over 1000, the Hazen-Williams coefficient C is the same as the Chesy's coefficient. Thus, the Hazen-Williams formula is accurate within a certain range of diameters and friction slopes. Okay, you can see it's a function of diameter and friction slope. So it is accurate within certain range of diameters and friction slopes, although it is used indiscriminately in pipe designs. But we should know that it has a limit, okay, as to the diameters and the friction slopes that it is applicable to. Like I mentioned before, for laminar flow in pipes, less than 2000, laminar, greater than 4000, turbulent, in between, transitional, or to turbulent, which is critical region. Okay, and for laminar flow, friction factor, which is F in the Westbank equation, is a function of the Reynolds number only for laminar flow. Okay, it's a function of the Reynolds number. It is given by this relationship, the friction factor 64 over RA. But normally flow in pipes is usually turbulent. Okay, this we mentioned before. In the turbulent regime, the friction factor is a function of the Reynolds number as well as relative roughness of the pipe. Okay, and Nikuradze published the results of now famous experiments on smooth, uncoated, and rough pipes coated with sand grains of uniform size. This experiment, when the results are plotted as the friction factor versus Reynolds number, we have figure 15.3. The roughness is characterized by a parameter K over D. That is the roughness of the inner side of the pipes. Okay, the roughness is characterized by a parameter K over D, where K is the average diameter of the sand grains and D is the internal diameter of the pipe. When you have a pipe, okay, it's coated with some sand grains here, okay, which to represent the roughness within the pipe. So K is the size of the sand grains and D is the diameter of the pipe. In contrast to the Nikuradze sand roughness. The roughness of commercial pipe is not uniform. As a means of differentiating the non-uniform roughness of commercial pipe, as a means of differentiating the non-uniform roughness of commercial pipe is designated epsilon, and is given equivalent sand roughness. Okay, so we use epsilon, okay, to represent, the roughness. Epsilon over D is given in equivalent sand roughness. Table 15.1 indicates equivalent roughness of pipe of different material. Epsilon indicates the roughness level of the pipe, the inner side. Okay. Based on the results of this experiment, the turbulent flow is further classified in 3 zones, as shown in figure 15.3. You have the flow in smooth pipe, where the relative roughness, this is called relative roughness, which is epsilon over D, is very small and plays an insignificant role in determining the friction factor. So here, for smooth pipes, of course, for smooth pipes, epsilon will be low. Flow in fully rough pipe, where viscosity's effect is insignificant on the friction factor. It's rough, but viscosity's effect is insignificant on the friction factor. And you have flow in partially rough pipe, where both the relative roughness and viscosity are significant. Now, this is table 15.1, which we have been referring to, which gives the roughness values for pipes. Okay, this is the equivalent roughness depending on the material. You can see PVC, plastic pipe, very smooth, so almost zero. Brass, copper, aluminum, glass, also smooth. By smooth, it means, the roughness is negligible, almost zero. Cast iron, it depends. Okay, galvanized, because new and old, it may be different. Okay, in some instances, because of deposition, okay, and deterioration of the pipe material, the roughness can increase over time. So you can see the roughness here increasing with concrete, riveted steel, and brick sewer. Here, riveted steel, concrete having, very high roughness, equivalent roughness. Okay. So the smoother it is, the less the roughness. The coarser it is, the more rough it is, then the more the roughness coefficient. And this is the Moody's diagram for determining the friction factor. Moody diagram for friction factor for pipes. Here you have 3 axes. You have the Reynolds number. You have the relative roughness. So once you have these 2 values, you can determine the friction factor, F. Okay, and depending on the flow type, you can see when flow is laminar, F is just dependent on the Reynolds number. But then you have transition zone, okay, and you have rough turbulent zone, okay, which is usually the case for our flows. Okay, so all you need to do is to determine the roughness, relative roughness, and the Reynolds number, and then you can now use it to know the friction factor. Let's assume our equivalent roughness is, let's say, 0.002. And let's assume the calculated Reynolds number is 10 to the power of 7. So what is the friction factor? All you need to do is to come here. This is the Reynolds number when this is logarithmic scale. Okay, it's not linear scale. The roughness coefficient is having a linear scale, but this one is having logarithmic scale. Okay, it is no, even the friction factor is not having a logarithmic scale. Yeah, no, it's not having a linear scale. So this is logarithmic scale. You can see from 1 to 9, then 1. This is 10 to the power of 3, 10 to the power of 4, 10 to the power of 5, 6, 7. Okay, meaning 2 here, it means 2 times 10 to the power of 6. 3 here means 3 times 10 to the power of 6. 9 here means 9 times 10 to the power of 6. 1 here means, you move to the next level, which is 10 to the power of 7. So this is how to read it. So to get our friction factor using the Moody's diagram here at Reynolds number 10 power of 7, we only need to draw our line, our vertical line, and then where does it cut? Relative roughness 0.02. This is where it cuts. This is where the relative roughness is 0.02. And then we now stretch it along the friction factor axis and read it. Okay, so in this case, the friction factor is going to be what? It's in between 0.022 and 0.024. So if this is, let's say, midway 0.03, so this is like 0.023. So this is like 0.0, maybe 0.0235. Okay, 0.0235. Okay, now what about, let's say we have the relative roughness not exactly corresponding to any of the curves here. Let's say 0.03. If the relative roughness is 0.03, how can we read of the friction factor? So in this case, you assume an imaginary curve in between 0.02 and 0.04, which will pass, almost halfway between 0.02 and 0.04. Okay, so we assume, another line, another curve of the relative roughness to be here, and then we read the friction factor, which will be 0.026. Okay, I hope it is clear because we will be using the Moody's diagram in the subsequent examples, but this is just like an illustration on how to use the Moody's diagram to determine the friction factor. We determine the friction factor, for the Darcy-Westbank equation. For the Hazel-Williams formula, we don't need the friction factor because the head loss formula for the Hazel-Williams equation is given in terms of, the Hazel-Williams constant, diameter, and the bed slope. All right, let's take a few minutes break. And when we come back, we look at this example. No, Amjad, it is in chapter 1. What we did about the, water distribution. All right, let's continue. Okay, here it says you have water that is delivered at a rate of 0.8 cubic feet per second by a 6-inch cast iron pipe at 80 degrees Fahrenheit between 2 points A and B that are 1,000 feet apart. Okay, if point A is 100 feet higher than point B, what is the pressure difference between the 2 points? Always when you have a problem, try to like sketch it to help you with understanding. This is point A, point B. Okay, and what has to be delivered between these 2 points that are 1,000 feet apart. Okay, 1,000 feet apart. If point A is higher, so the difference in elevation, this is 100 feet. What is the pressure difference between 2 points? Okay, so what is the difference in pressure between the 2 points? And we are to use a pipe, and the flow rate is 0.8 and the size is 6-inch. Okay, so here I'm putting the head loss in the pipe to find the head, because as water is flowing, there will be head loss in the pipe, isn't it? And to know exactly the pressure difference, we need to remove the head loss from the pressure head, okay, or from the total head. Okay, we need to subtract the head loss, because like as the water is flowing, okay, let's say the piezometric head, so there will be the head loss. Okay, so we need to determine the head loss so that we can now find the pressure difference. Okay, and to determine the head loss, we need to get the head loss due to friction, HF. Okay, and to get HF, we need the velocity in the pipe, which we don't know, but we can find it because we have the flow rate, Q. Q over A is the velocity of flow, okay, which is this. And then, so we can get V, length of the pipe, can just assume that, the 1,000 feet is the length of the pipe, okay, which is L. The diameter is already given. And then F, we need to find F. To find F, we need the Reynolds number and the relative roughness so that we can use the Moody's diagram, okay? The Reynolds number, VD over mole, now we substitute, you can see this is the Reynolds number. And the value of the Reynolds number, this is 2, which is 222,000. You see, this is turbulent, very turbulent. Greater than 4,000 is turbulent. So this is 222,000. So the flow is highly turbulent, okay? And then the relative roughness for the kind of the pipe, for cast iron pipe, we go to that table and get the relative roughness. For cast iron, old or new, this is the relative roughness, epsilon, okay, which is 8 to the power of minus 10 to 8 times 10 to the power of minus 4. Okay, so that was where we got this value, okay, because it is cast iron. And then this is the diameter, pipe diameter, okay. So we now go to the Moody's diagram. For this Reynolds number at this relative roughness 0.016. 0.016, 0.0, what is the value? 0.0016. 0.0016. So where is it going to be? This is 0.001 and this is 0.002. So where is 0.0016? So 16 will lie somewhere more than halfway. Okay. Maybe somewhere here. Okay. And then what about the Reynolds number? 2.2 times 10 to the power of what? The Reynolds number is 2.2 times 10 to the power of 5. Okay, so let's locate it. So we got 10 to the power of 5. This is 10 to the power of 5. So this is 2 and this is 3. So 2.2 should be somewhere here. Okay, because this is 2.25 and this is 2.2. So we now sketch. Okay. We draw a vertical line. Where is my ruler? Up. We draw yeah. Want to draw a vertical line up. Okay, and then this is 0.016. So we assume a curve because there is no specific curve passing through, and you can see the curve. Okay, so we assume an imaginary curve. Okay, that is passing through. Okay, like this, and then where they meet, we now trace it to get the friction factor. Okay, so approximately 0.023. Okay, or something like that. Yeah, you can see 0.023. So the friction factor is approximately 0.023. Okay, and then from there we can determine the head loss due to friction. And once we determine the head loss due to friction, we now use it, to get the pressure difference. Okay, the difference in elevation, if this is the datum, so it becomes 0. Okay, and then if here this is 0 here, then in this case this is Z1 is the pressure. Okay, if we neglect the velocity also, velocity is so called, but so here we are not neglecting, but we are assuming they are equal at both points, so they will cancel out. The velocity head at both points, meaning the velocity is uniform because this is pipe. Okay, this is pipe. It's not from, let's say, a reservoir to a pipe, so we can assume the velocity to be constant throughout. So we have the pressure, the static pressure that we want to find. Okay, and we can make it the subject of the formula, P2 minus P1. You can see here the driving force. Simply, the driving force for fluid is what? Pressure difference or pressure gradient, which is a simple question that can be asked anywhere. Okay, what is the driving force for fluid flow? Is pressure difference or pressure gradient. So you can see P2 minus P1. So this is the pressure in pound per square feet. Okay, and this is pound per square inch. Okay, I hope it is clear. Now we talked about the minor head losses, which we said they really, are in existence, except that they are so small compared to the major head losses, which is the friction head loss. Okay, so that's why more often than not we neglect them. Okay, so in addition to the continuous head loss along the pipe length due to friction, local head losses occur at changes in pipe section. Okay, at changes in pipe section and bends, because pipe section here, it can be a decrease in the pipe section, and it can also be an increase in the pipe section, expanding section. Okay, in both ways you have head loss. Okay, and you have at bends, whenever you have bends, whenever you have valves and fittings. These losses may be disregarded for long pipelines, but are significant for pipes that are less than 100 feet long. Okay, for long pipelines, the friction head loss, dominate, because the friction head loss is also proportional to the length of the pipe. Okay, so for long pipelines we can neglect them, but for pipe less than 100 feet in meter, that is 30 meters. Okay, since pipe length in water supply and wastewater plants are generally short, that's less than 30 meters. Okay, so minor losses are important. Okay, and there are two ways to compute these losses. One, in the equivalent length technique, a fictitious length of pipe is estimated that will cause the same pressure drop as any fitting or change in a pipe cross section. What are we saying here? We say equivalent length technique. Here we have a fictitious, meaning imaginary length of pipe is estimated that will cause the same pressure drop as any fitting or change in a pipe cross section. And this length is added to the actual pipe length. Okay, so this length is added to the actual pipe length. So meaning we are making it longer. We are increasing the length of the pipeline by adding an additional length that will take care of the pressure drop within the pipeline. Okay, and in the second method, the loss is considered proportional to the kinetic energy head given by the following formula. Okay, the minor loss is proportional to the kinetic energy head given by the following formula. So Km is the summation of all loss coefficients, okay, where V is the mean velocity of flow, and Km is the coefficient of the minor losses, okay? When you sum them up, summation of all loss coefficients. So here we consider that the minor loss is proportional to the velocity head, okay? And even the major loss is proportional to the velocity head, because when you have the friction factor F, L over D, V squared over 2G. This is the velocity head, okay? F, L, D, all these are constant. So even the minor loss is proportional to the velocity head, V squared over 2G, okay? So the general form of the friction head loss, is that the friction head loss is proportional to, this is V squared, isn't it? If you change V using Q over A, so you can see that the friction head loss is proportional to Q, in this case, N, to the power of N, which can be Q squared for the that's Westbank equation, okay? And when we, so this is like the general relationship of the frictional head loss is equal to KQN, where K is called the resistance factor, is a coefficient, and N is equal to 2 for that's the Westbank equation, and is equal to around 1. Can be different for another head loss formula, but for that Westbank equation, N is equal to 2. So K is called the equivalent resistance, okay, and it is given in table 15.2, and N equal to, like I said, for the Westbank equation, and 1.85 for the Hazel-Williams equation, okay? It's 1.85 for Hazel-Williams equation. So when you use the Hazel-Williams head loss formula, N is 1.85, and when you use the Westbank head loss formula, N is equal to 2. Okay, and it is equal to 2 because HF is equal to V squared over 2G. So we substitute V as Q over A. You know, this will be Q squared over A squared V squared. Okay. Now this is the table that gives the minor head loss coefficients. Okay, depending on the item: entrance from tank to pipe, flush connection, projecting connection. You can see the head loss coefficient 0.5, 0.81. Exit from pipe to tank. From pipe to tank, 1. Sudden contraction. Okay. A sudden contraction when D2 over D1 equal this. Okay. Sudden enlargement, 90 bend and 180 return threaded, 45 bend threaded. You know, all T threaded, through flow, branched flow, T flanged, you know, all the different valves: globe valve, angle valve, gate valve, check valve, butterfly valve. All these are the loss coefficients. Okay. So we will take example in which we have to use this table to get some of these coefficients and use them in calculating the total head loss. Now, for K, you see here, this is the K, which is the equivalent resistance from the general head loss formula due to friction. So equivalent resistance K for pipe has the following units of measurement. Depending on the units of measurement, you use this. Okay, for Darcy Westbank, if you're using the SI unit, you use this. For Hazel Williams, if you're using the SI unit, you use that. Okay. For Darcy Westbank, how did we obtain this? It is simply from the Darcy Westbank formula. HF equal F L V squared over 2GD. And then we substitute V equal Q over A. V equal Q over A, and A is for pipe is pi D squared over 4. Okay, so in this case, V is equal to Q over pi D squared over 4. So 4Q over pi D squared over 4. So when you replace V with 4Q over pi D squared over 4, and then you will arrive at this one, FL Q squared over 12.1 d to the power of 5. Okay. Already here you have d, and then here you square it. Don't forget, you square it. Okay, so d squared will turn out to be d to the power of 4. So this will be this. Okay, then the constants 12.1 is simply, here you have 16 over pi squared over times g times 2. It will give you 12.1. Okay, so it's simply add q squared here, and this is HF. Okay, so this is how this was obtained. So this is called the equivalent resistance. So that is why this is now simplified as simply KQ squared. What is K? K is FL over 12.10 d to the power of 5. Simple. We will also use this table in some of the examples to come. Now we will go into the design of single pipelines. Okay, and in the design of single pipelines, here application is made where it's made of the energy equation and the Darcy-Weisbach or Hazen-Williams equation. Okay, and minor losses relation as demonstrated in example 15.6. Okay, so how do we design a single pipeline? We first try to determine the total head loss using the energy equation, and then determine the friction head loss using either the Darcy-Weisbach equation or the Hazen-Williams, and compute all loss coefficients, meaning minor losses. Okay, include all minor losses where necessary, and then assume F and compute D by trial and error. Okay. Assume F, the friction factor, and compute the diameter by trial and error, and obtain F from the Moody's diagram to see if it will be different from the assumed value. If it is different from the assumed value, if it is so much different, then determine D again using the new F and obtain a new F from the Moody's diagram until F stabilizes. This is better demonstrated using an example which I'm going to explain below. Okay, that is the design of single pipelines. Now, this example, we have two reservoirs connected by a 200 feet, okay, two reservoirs, one here, one here. They are connected by 200 feet long cast iron pipeline. If the pipeline is to convey a discharge of 2 cubic feet per second at 60 degrees Fahrenheit, what diameter of pipeline is required? So we want to know the diameter of the pipeline to be used. We know the flow rate that we want, okay? And we want to know the diameter to be used. So to do that, we apply the energy equation. You know, look at the energy grid line and the hydraulic grid line. You can see here, because this is for the energy grid line, and the dashed one, less bold, for the hydraulic grid line. Here there is entrance loss, like I said. So that is why, you know, the pressure head did not start, or the hydraulic grid line did not start from here. Okay, ideally someone would think that it will start from here and move, and then the velocity head will now be like will start above it. Okay, but because there is loss, the pressure head here will begin at this point because of the loss, entrance loss into the pipe. You can see it. Okay, that loss may be different if you have rounded, smooth rounded, or you have sharp edge. Okay, for sharp edge, the loss will be higher than when it is rounded. Okay, so this is the pressure head, and this is the energy grid line. Here there is a bend, 90 degrees bend. There is also another loss, and that is why you can see at this point the pressure head goes down. You can see from here to here. There is loss of pressure head due to the loss, due to the minor loss as a result of the 90-degree bend. Okay. As a result, also the velocity head or the energy grid line will go down. Okay. And then as it is flowing, you have a globe valve here just before the entrance. There will also be loss in head, the pressure head, as well as the energy grid line. Okay. And then when it enters, then there is entrance loss here. Okay, there is entrance loss. Okay, there's entrance loss here. Now, the difference between the elevation is 20 feet, which gives the total head loss. Okay, which gives the total head loss. We can even do that without, you know, doing all this analysis, because this is the pressure head here, and this is the pressure head here. So the difference between them is the head loss. Okay, because it means ideally the pressure head should be up to this point, because it should be parallel, isn't it? Ideally, without any head loss. Okay, the pressure head in this tank should be up to this point, but because of the head loss, the pressure head is dropped, is brought down, is reduced from here to here, because of the head losses that occurred due to major head loss frictional force factors and due to the minor head losses. So by looking at it without doing anything, you can say that the head loss is simply the difference in the elevation. Okay, it's simply the difference in the elevation, because ideally the pressure head is supposed to be maintained if not for the losses. The losses are what reduce the pressure head. from this level in this reservoir to this level in this reservoir. And this is proved using the energy equation, okay, applied between points 1 and point 2, okay. When you take the datum to be 0.2, okay, so this is 0, so this Z1 is 20. The pressure is atmospheric in both cases, which is 0, so they cancel. The velocity also negligible at both points, okay, so the velocity also gone. Okay, not the velocity in the pipeline. We are talking about the velocity here and the velocity here in the reservoirs, okay? And then you have simply the head loss being equal to the elevation, okay, which is 20 feet. Now we know the head loss. How do we determine the diameter? When we substitute here, you see, using the imperial units for the Darcy-Weisbach equation, we know the length, we know Q, we know the diameter, but we don't know, yeah, we know Q, but we don't know F and D, okay? No, we don't know the diameter. In fact, that is what we want to know, okay? We know L, we know Q, okay? So we don't know F and D. So two unknowns in one equation, okay? And don't forget, not even one equation. This is HF, because this is the total head loss, which comprises the frictional head loss and the minor losses. Okay, so this is the total head loss. So this is HF only, and then the minor losses will be the sum of the entrance loss plus bend loss plus valve loss plus exit loss. Okay, which is summation of kV squared over 2G. Okay, so what is K? What is K for entrance loss? What is K for bend loss? What is K for valve loss? K for exit loss. To get the K values, we go to this table. This one. Entrance loss. Okay. Entrance loss, entrance from tank to pipe, you can see. Flush connection. So we use 0.8. Exit from pipe to tank. Okay, which is 1. From pipe to tank, which is 1. Okay. And then we use globe valve. Coefficient is 10. And then we use 90-degree bend. Okay. Flange, return flange, 90-degree bend. Okay, which is I think 0.3. So we now go and add all these losses here. Yeah, you can see them. The entrance loss 0.5, exit 1, 2 90-degree bends at 1.5. There are even 2, I remember, not 1. 2 90-degree bends at 1.5 each, so 3. Glove valve 10. So the total coefficient 14.5. So now the total head loss is now this plus this. Okay. Q is known, so we have F and D. One equation. And how can we solve this? We have to use trial and error. That's why we need to assume F. So we assume F to be 0.03 here. To substitute here and find D. And we found D 0.59. So now we will use this D found to compute F again using the Moody's diagram. Okay, from this diameter we can find the area, the velocity and Reynolds number, and the relative roughness. Don't forget how we got epsilon, okay, the equivalent roughness from that table, okay, depending on the pipe type. So we use the Moody's diagram using the relative roughness and the Reynolds number to get F. We assume it to be 0.03, but when we got D, we found it to be 0.0215, okay, which is different from 0.03. So that means we use this value again to find new D. It's an iterative procedure, okay? We use this value to find new D. So based on the revised value of F, our new D, it was 0.59 before, now it is 0.57. So we now go through the same process and get a new F from the Moody's diagram, which is 0.0215, which is almost the same as what we got before, okay? So in this case, we accept the diameter. Don't forget, we want to find the diameter. That is the design, okay? Design is usually finding dimension, isn't it? A given dimension, you know, a given dimension, depth, height, size. If it's reinforcement, you know, the reinforcement bars, the diameter, the depth of the column, the height of the beams, and all that. So that is all about design. And you can see design sometimes it's not an explicit procedure. It's like, you know, going back and forth, changing this, changing that, until you get to the required result, okay? So with this, we now use the diameter as 0.57 feet. If F were to be different from the previous one, if they differ so much, we now revise it and then find new F until the difference is so small, okay? My time is up, and I will stop here. And then in the next class, we will take the design of single pipelines with pumps. This design of single pipelines without pumps, you know, just flowing by gravity. So what about when you have a pump? What changes in the design? Okay, this we shall see in the next class. Any question? All right, see you today for the lab. Come early because we will do 2 labs today. Okay, come early.